A 1972 Maytag A806 is still washing clothes after outliving 3 newer machines. That should not sound possible, but it fits the joke Maytag built its reputation on, the repairman whose phone never rang. This machine was not magic and it was not failure-proof. Its secret was simpler. When something wore out, the damage usually stayed small, reachable and fixable. Modern washers often fail differently, turning one bad part into a replacement decision. In Newton, Iowa, in 1972, the Maytag A806 sat near the top of the company's home laundry lineup. It was a premium top loader with chrome trim, a squared-off control panel, mechanical timer dials, and a porcelain-coated wash basket built to resist rust and staining. Inside, it used Maytag's Power Fin Agitator, a tall center post with fins designed to roll clothing through the water instead of just stirring it in place. Everything about the machine felt substantial: the cabinet, the lid, the transmission, and even the sound it made when the cycle shifted. That weight became part of the legend, but weight alone does not explain survival. Plenty of heavy appliances still broke, leaked, or were thrown away when repairs stopped making sense. There is also survivorship bias. The A806, still running today, is the one that made it. It does not prove every washer from 1972 was indestructible. It proves something more useful. This machine came from an era when repair was expected. On the A806, diagnosis starts with 2 screws. Remove them, lift off the front panel, and the machine stops being a sealed appliance. The major working parts are right there in front of you. The motor mounted low in the cabinet, the drive belt, the pump belt, the rubber hoses, the suspension springs, the water pump, the brake, the clutch, and the transmission. But the console, the same logic continues. The timer is a mechanical control with contacts and cams. The pressure switch is a separate part connected to a small air hose from the tub. If the washer will not fill, will not drain, will not spin, or will not shut off, the path from symptom to suspect is visible. A leak points you toward a hose, pump seal, or tub connection. A no-spin complaint points toward belts, clutch, brake, or motor. A fill problem sends you to the inlet system or pressure switch. You do not need a laptop, a diagnostic subscription, or a software decision tree to begin. That layout was not primitive. It was an intentional service architecture built so a person could open the machine, understand the system, and replace the failed part. The heart of this Maytag was a reversible motor driving 2 belts. When the motor turned one direction, the transmission agitated the load. When it reversed, the pump moved water out and the drive system prepared the basket for spin. That reversal was not electronic trickery. It was a simple mechanical change in direction that made one motor do 2 jobs. The spin cycle depended on Maytag's helical drive system. As the motor came up to speed, the drive pulley and helix helped release the brake, then brought the basket into motion gradually. The belt did not grab instantly with full force. It slipped in a controlled way, letting the heavy wet load accelerate without shocking the motor, transmission, or brake assembly. That slip was part of the design. If the machine was overloaded, or the pump was stiff, or the basket resisted spin, the belts complained first. They squealed, glazed, stretched, or eventually broke before more expensive parts took the hit. That is why a simple belt kit mattered. The common wear parts were outside the sealed transmission, reachable from the front and replaceable directly. In this system, failure was not always a disaster. Sometimes it was a cheap belt doing exactly what it was there to do. Open a Maytag parts book from the early 1970s and the machine is not treated as one sealed appliance. It is broken into systems: the cabinet, tub, agitator, damper, brake, pump, motor carriage, belts, timer, lid switch, transmission, and wiring harness. Those exploded diagrams mattered. A repair shop could identify the failed piece, order just that part, and leave the rest of the washer alone. If the damage was larger, the same literature showed where a complete assembly could be swapped instead. The choice depended on the failure, the customer's budget, and how much labor made sense. That is very different from many modern repairs, where a fault can point to a molded module, a sealed board, or a factory-built assembly that is not meant to be taken apart on a workbench. The technician replaces the black box, not the worn contact, spring, pawl, or seal inside it. Even the heavy transmission in the old Maytag was serviceable in the larger sense. It could be removed from the machine without cutting the tub apart or destroying the cabinet. That did not make the job easy, but it kept one major failure from automatically condemning the whole washer. This design was not perfect. Seals leaked, bearings wore, timers failed, porcelain chipped, cabinets rusted, and today many parts depend on donor machines. But the original parts book shows the philosophy clearly. Repair was not an afterthought. It was printed into the machine's anatomy. A modern washer is not just doing the old job with newer parts. It is being asked to use less water, spin faster, make less noise, protect fabrics, meet efficiency rules, and fit into homes where people expect quiet operation and digital controls. That changes the machine from the inside out. A front loader may have a plastic outer tub, a stainless inner drum, a high-speed motor, shock absorbers, a door lock, water valves, temperature sensors, pressure sensing, a drain pump, and a control board deciding when each part should act. Instead of filling a deep tap and moving clothes through a large volume of water, it has to calculate how much water the load can absorb, tumble it efficiently, and then extract moisture at very high speed. The electronics are not automatically bad engineering. The control board and inverter can ramp the motor smoothly, reduce energy use, detect an unbalanced load, pause a spin before the cabinet walks across the room, and adjust cycles for different fabrics. Sensors help prevent overheating, overfilling, and unsafe door opening. These systems make modern washers more flexible, more efficient, and often much quieter than their ancestors. The problem begins when the failure is small, but the repair boundary is large. A sensor error, a cracked plastic fitting, a locked drain path, or a board fault can lead to an expensive assembly replacement. The machine became smarter because the problem got harder. But its complexity also changed what repair means. The clearest example is the rear drum bearing. It is not glamorous, it is the kind of part people understand instantly. A ring of steel, grease, and rolling elements that lets a shaft spin smoothly under load. In a washer, that bearing supports the shaft connected to the inner basket. Every spin cycle pushes water, clothes, and imbalance through that point. When the bearing wears out, the first clue is often a low growl during spin. Later it becomes a roar, then wobble, then leaks as the seal fails and water reaches places it should never go. On an older serviceable design, the repair boundary was close to the failure. Open the cabinet, split the tub, pull the basket shaft, replace the bearing and seal, then reassemble the machine. It was not always easy, but the dead part was the part you changed. On many modern machines, that boundary moved outward. The tub may be sealed, welded, or bonded. The bearing may not be listed as a separate service part. Instead of buying a bearing and seal, the repair can become a complete rear tub or an entire wash module with the basket, outer tub, sensor, pulley, and mounting points already built in. That is how a small mechanical failure turns into half a washer. The original problem is still a worn bearing, but the official repair throws away plastic, steel, electronics, and molded structure that may be perfectly usable. Clever packaging saves time at the factory. It stops feeling clever when one worn ring of steel condemns everything around it. At the kitchen table, the design shows up as an invoice. A technician does not begin with the price of a bearing. They begin with a service call, a diagnosis fee, travel time, insurance, fuel, tools, and the cost of standing behind the repair if the machine fails again next week. Before one part is ordered, the visit may already be over $100. Then the parts list appears. A control board can cost $200 or more. A drain pump may be reasonable until labor is added. A sealed tub or wash module can push the estimate into the range where the customer stops listening to the repair and starts shopping for a replacement. This is the $700 washer problem. The machine may have sold new for $700. A failed bearing, locked inside a tub assembly, can require a part that costs several $100s, plus 2 or 3 hours of labor. The final estimate can land close to the original purchase price. From the technician's side, that estimate is not a scam. It is risk pricing. If the tap job takes longer than expected, if a brittle hose cracks, if an electronic fault appears after reassembly, the callback belongs to the shop. Marginal machines become financial traps for both sides. That is why many repair people use the 50% rule. If the repair costs more than half the price of a comparable new washer, replacement becomes the practical recommendation. At that point, the machine has not just broken mechanically, it has crossed an economic line that its own design helped draw. The old Maytag's biggest weakness is not hidden in the transmission. It is printed on the water bill. A Maytag A806 could use roughly 36 gallons of water on a large load cycle. A modern Energy Star washer often uses far less, sometimes under half that amount, depending on the design and cycle. For a household running about 300 loads a year, that gap can mean several thousand gallons annually. Over a decade, it can become tens of thousands of gallons. Water is only part of it. If those loads are warm or hot, the older machine is also asking the water heater to do more work. Then the clothes leave the washer wetter, because the final spin is slower than many modern machines. More water left in the fabric means more time in the dryer, and the dryer is often the real energy hog in the laundry room. Modern washers also gained capacity. A larger drum can reduce the number of loads a family runs. Front loaders can be gentler on fabric because they lift and tumble clothes instead of relying on a central agitator to pull them through the water. So the efficiency argument is real. The nostalgic machine is durable, but it is not free to operate. The important distinction is that saving water and energy does not require sealed tubs, disposable bearing assemblies, or machines designed to be uneconomical to repair. Before you buy a washer, look up the exploded parts diagram for the exact model. Check whether the bearings, tub halves, pump, door lock, control board, and suspension parts are sold separately, or only as expensive assemblies. Then read the warranty like a repair bill. A 10-year parts warranty may still leave you paying the labor, and labor is often the reason a machine gets scrapped. That is the real Maytag lesson, not old versus new. It is whether one failed part can remain one ordinary repair. Paul Lonely stood beside a silent phone because Maytag sold a promise. Failures should be rare, and when they came, they should stay small. That is why the 1972 washer survived. It was not immortal, it was repairable. Thanks for watching. Comment with the appliance you wish still worked this way, and subscribe for more breakdowns of design, repair costs, and hidden trade-offs.